All right, welcome to the video lecture series on Introduction to Computer Networks, and today's topic is going to be transport and application layer in the TCP/IP model. So, let's refer to the model that we have been looking at so far. In the far left, you've got the OSI model, which consists of 7 layers, starting from physical up to the topmost level, which is application. Then you have the two versions of the TCP/IP model. The older version had 4 layers: link, internet, transport, and application. And the newer TCP/IP model has 5 layers, where the link layer has been broken down into 2 layers: the physical, the data link, and then the rest of the layers are the same. That is the network, transport, and application. So today we are going to look at the top 2 layers, the transport and application. So far the lectures have been covering bottom up approach. So we'll cover the transport layer first, and then we'll talk about the application layer. So the transport layer provides logical communication between applications which are running on different hosts in the network. It's not necessary that these hosts are running in the same network. They could be far across the world, running in 2 different networks, and they're connected with multiple other networks in the middle. However, in most cases, we will see that hosts are running different applications, and these applications are those are communicating to provide some form of service and feature to the user. So the transport layer provides this specific logical communication between the applications which are running on the hosts. For example, if you are running a chat application, let's say Skype, and then you are chatting with another user on Skype in another part of the world on his or her computer, these two applications are able to communicate with the help of transport layer. Do note that all communications actually occur through the network, and the data which are being transferred from the application, that is Skype, go through all the layers, which is what we refer to as adjacent layer interaction. So it goes from the application layer to transport, the network, then link, and then physical layer, and then goes across the network, across multiple devices, reaches the destination, enters into the physical layer, and goes up from the physical to the link, then the network, then the transport, and then the application layer where the destination Skype application is running. In addition to this communication, it provides other features such as data delivery, error correction, some form of quality control of the communication that is occurring during the process of execution of the applications. Another interesting thing which the transport layer also performs is what we call the order of delivery and flow control, which means that at a given time the network could be overloaded with packets which are being transferred from other hosts. At the same time, one given host or computer could be communicating with many other applications over the internet. So the interface could be overloaded with network communication due to other applications which are running. So all of these overload and the congestion that we have at a given moment, to ensure that we have effective communication, transport layer comes into play to ensure that specific order of delivery and to ensure proper delivery of the packets and data. Um, Another very useful application or operation that the transport layer performs is what we call multiplexing of data transmission between network hosts. Uh, the concept of multiplexing is due to the fact that a given host is not communicating over the internet with respect to only one application at a given time. In most cases, there are multiple applications. Just think of any given scenario when you are using the internet. You are probably browsing Google from your web browser. Then you have uh, Skype running on your computer, and then you have uh, Dropbox running in the background, which is syncing your files, and all of these applications are running at the same time on the same host. So the concept of multiplexing is here because one host is responsible to transfer all of this data, but there are multiple applications running on a single host. So this multiplying of channels is what we call multiplexing, and the transport layer is able to identify which application should be receiving which packets. The PDU for the transport layer is something that we refer to as segments or datagrams. Both of them are okay. In some cases, segments are more commonly referred. Datagrams are commonly used as well. So we use both of these terms as the protocol data unit for the transport layer. So the transport layer uses a different form of addressing compared to what we have already seen so far. That is the MAC address in the link layer and the IP address in the network layer. Compared to that, the transport layer uses what we call port addresses to identify applications on hosts. So these addresses are logical. That means that it doesn't really have a physical existence, and this is completely managed by the operating system. So to sum up the concept of port addresses, every application that you run, every instance of an application that you're running on a host will have a port address assigned to it. The different types of communication in the transport layer allows both connection-oriented and connection-less, two specific protocols, TCP and UDP. We will be looking at it in the later part of this given lecture. And the basic idea is that different applications require different kinds of performances and guarantee. And these protocols allow different features to be incorporated into the applications. So something very familiar that we've already looked at so far in the way that the protocol data unit is created. So the transport layer receives the data from the application layer. So the application layer PDU is basically the data from the application, and then the transport layer adds the transport layer header and creates what we call the segment of the datagram. So this is the protocol data unit for the transport layer, which is then passed on to the network layer. So if we try to look at how the datagram or segment created by a transport layer looks like, we have this concept of ports, right? So that's what we have already established. So when there are applications communicating over the network, so there is a source application and a destination application. And for that, we have, for every packet that is being transferred, for every piece of data which is being transferred, we have a source port and a destination port, right? And for this particular example, you will see that Alice's laptop with an IP address of 10.0.0.1 is running three different applications. She is streaming music over the internet. She has a Wi-Fi document scanner, and she's also doing some Google search for whatever reason. So if you look at the way that these information are organized, there is a source IP, which is the source of the streaming music website, and the destination sorry, this is actually supposed to be destination IP. So the destination IP is Alice's IP. The same here, the source IP is the document scanner's IP, and then you have the IP address of Alice, and then you have the source IP of Google, and then you have the destination IP of Alice. For each of these applications, you will see that there are different ports. So the source port here is 33, which means that the website which is streaming the music, the application for that is running on port 33 on that host. And the destination port on Alice's laptop is 1024, where that particular application is running to play the music. The source port here for the document scanner is 1245, and the destination port that receives that scanned document on Alice's laptop is 1023. Same here, so the destination port here on Alice's laptop to receive the Google search or to perform any form of actions is 1024. So the concept that we try to grab here is that multiple applications running on Alice's laptop, whatever packets which are coming in or going out will have the same IP address but different port addresses based on whatever application that packet belongs to. So if we look at the overall concept here, if we have two hosts communicating with each other, the hosts have IP address, the hosts have MAC addresses. So let's say Alice has a MAC address here and Bob has a MAC address here, and then each of these are physical addresses assigned to the network interface. This occurs in the link layer. Next, in the network layer, the hosts Alice and Bob get assigned logical addresses in the network layer, which are IP addresses, as you can see here. And then the host, Alice, as well as Bob, they have multiple applications which are running on that same machine. So each of these applications will have ports assigned to it, which are communicating with the network interface on both hosts. And that is how the Skype, which is running on Alice's PC, is able to communicate with the Skype application that is running on Bob's PC. And if you can see here, it doesn't really matter if you have the same port address on both hosts because they actually belong to different IP addresses. So port addresses are provided by transport layer protocols, and it is managed by the operating system. So the operating system determines what and where the traffic should be directed. That is, which application should be receiving a given piece of data as it receives the data from the network interface. And the concept is that, the operating systems have a bunch of port addresses, and that allows a single host to have a single IP address but still be able to run multiple network applications on the same machine. And each port identifies a distinct and individual service that the host can have running on itself. There are three different kinds of ports. The number allocation for these ports is regulated by what we call the Internet Corporation for Assigning Names, or the ICANN organization. Names and numbers. And so there are three different kinds of ports. First, we refer to what we call as the well-known ports. They range from 0 to 1023. Do note that all hosts which are a part of the network will have these regulations applied to it. And this is a standard that we try to follow. So the well-known ports range from 0 to 1023, and these are assigned to common protocols and services which are basically standardized. So let's say if you have HTTP running on your machine, that is assigned a port address of 80, and so on and so forth. So there are very common standard protocols which run almost on all network hosts, and they are assigned IP addresses within this range. Next, you have registered ports, which range from 1024 to 49151, and these are ports which are assigned to user processes and applications. So these are rather free to use when you are developing a network-based application. So let's say Skype would use a port from this range. If you have any other network application, let's say Dropbox will be using a port within this range. And this port is allocated, requested by Dropbox to the operating system of that machine, and the operating system assigns that port to Dropbox within this range. And finally, you have the dynamic. It's also called the private, but dynamic makes more sense. So this is the range of ports which vary between 49152 to 65535, which is the max limit. And these are ports which are assigned dynamically when a specific port is not required. So these are more temporary compared to the registered ports, and they apply to user-based services and applications as well. So let's say you are trying to run an application which just needs to send one packet, and then it will shut down the port. In this kind of cases, the dynamic ports are allocated, and it applies more to UDP protocol. Something that we'll see later is unreliable and does not guarantee delivery. So therefore, the operating system is constantly refreshing the allocation of dynamic ports within this range. So it is assigned, an application is assigned a port within this range when a session is requested, and then immediately released when the session ends. So let's see a sample scenario how these ports come into play when multiple hosts are communicating over the internet. So let's say we have 4 hosts connected to a very large network. They are in different parts of the world. 2 of them are user terminals, Alice and Bob. Let's say they have laptops running and connected to the internet. And then you have 2 hosts which are servers. In this example, the YouTube server and the Skype server. And they are also a part of the internet and some other part of the world. And as you can see, their IP addresses are completely different, which signify that they belong to different parts of different networks, right? So the initial state is that all of these devices are a part of the network. However, none of them are actually able to communicate with each other because they don't have any applications which have been allocated any ports, and none of the ports are open. So although they are physically connected, maybe directly or across multiple networks, they are still not being able to exchange meaningful data between any of the 2 hosts. So let's say Alice, the host Alice, the operating system, assigns and opens the port for a web browser tab. So every tab on the web browser opens a port, and the port is open on Alice's machine. However, it still is not being able to send or receive any data because there are no other ports with which it can communicate. So we can say that to have a meaningful communication or conversation with any other host, there should be another port open for another application on another host. So in this example, let's say web browser tab 1 is trying to play a YouTube video. So the YouTube server will need to open a port on that machine, and then these two ports can start exchanging meaningful data between these two hosts. So Alice could be requesting for a specific video, and then the YouTube server could be sending the video into that specific port on Alice's machine, and then that port will then put it together as a video and will be playing it on the web browser. However, as you can see here, Bob still does not have any of the ports open, and Alice does not have also any of the ports open. So there's no other communication happening within these hosts apart from the YouTube video. So to have a meaningful conversation in a real life scenario where Alice would be, let's say, having a video played and also chatting over Skype with Bob, in that case, the Skype port on Alice's host should open, which will then have the exchange of meaningful data with the open port on the Skype server, and then the Skype server will also be communicating with the open port on Bob's host to have the meaningful exchange of data. So now Alice is at the same time playing a YouTube video and also communicating with Bob over Skype using the same single IP address, but multiple ports. The same applies to Bob and YouTube and Skype.